All right, so I've got a worksheet here. Maybe you can screenshot that. Is that page 1? Yep. And that's what we're working on today, just the first half of this. First 20 problems, because I want to do a little explanation on a new topic. I want to talk about inverses. And we still have to do volumes of revolution. We got to look at the inverse tan functions. There's a nice video on that, I think, in the playlist. So you might want to get a jump on that, because I think I might do a little explanation here, but it's a video that's already done. So maybe I'll just assign it as in. If you want to learn it, go look at that video on the playlist. Related rates and max mins, we'll probably use a lot of the videos that are already done on YouTube for those, because it'd be hard to do on this board. Geometric integration, I'm going to do some different kinds of constructions of different shapes, and changing the limits of integration. And I'd like to get those in front of us in the next week or so, and that's a lot of material, a lot to digest, and we're just going to chip away at it. We're going to integrate it. We're going to do a little bit each day and accrue some knowledge and some conceptual awareness. That's what we're going to do. All right, and hopefully that'll strengthen foundations. I actually asked, well, I'll get to those in a minute. So let's say we have F and G are inverses. Just say they're inverses. And I've already kind of prepped you with this, whether you realize it or not. But F of 3 gets us 4, and F prime of 3 gets us 5. Why don't I write 5 over 1? Then can you tell me something about G? Pause the video every time I ask a question, right? Well, I think you switch the x's and the y's when you first start looking at inverses. So G of 4 gets us 3. And it turns out that if you take a derivative, you're really looking at y2 minus y1 over x2 minus x1, starting in algebra 1, right? Linear function. That's the only one you worked it with, was the linear function. And that's kind of what we do. We compare the change in y to the change in x. We just do it at an instant. So calculus is like that microscope, dx, change in x, 0.001. All right. Oh, if you change the x's and the y's, then down here, it would seem that x2 minus x1 should get us y2 minus y1. Wow. So I think if 4 gets me 3, and over here a 3 gets me 5 to 1, then I think over here the derivative at 4 is going to give me 1 to 5. Well, let's see if that's true with a couple of inverses. Let's use x squared. I've done it, but for x greater than 0. So we're just going to look at x is greater than 0. Here's x squared. And I know at 3 I get a 9. So g of 3 gets me 9. And I know my slope of x squared is 2x, so f prime of 3 gets me 6. And I think I know the derivative of x squared is the square root of x. And I think a 9, square root of 9 gets me 3. The square root of 9 gets me 3. And I think the derivative of the square root of x is 1 over 2 root x. And I think g prime of 9 gets me 1 over 6. Very interesting. Well, what happens if we have a derivative, or we have a function whose inverse is kind of difficult to write? Let's say we have, for f of x, how about we do x cubed minus 2x? Okay, and I told you I want to find g prime of, let me write g prime over here, g prime of 980. Well, you're going to have to use your fingers on this one and count. How do I get 980? Because I shouldn't have erased that yet. I should have looked at f of 3 equals 4 and g of 4 equals 3. Okay? The output of f is the input of g in this instant. So we really want to find out when this thing equals 980, and I'll give you situations where it's not going to be hard to see. I think you can see that f of 10 f of 10 gets us 980. And we can find the derivative of this. 3x squared minus 2 at 10 is 300 minus 2, 298. So f prime at 10 is 298. I think we're ready to say that g of 980 is 10 and g prime of 980, it is 1 over 298. Now there's a fancy formula for that. That's very confusing when you first look at it because it's a tongue twister. But rather than use the formula to get an answer, why don't we build up towards the formula, and then we'll put the formula on the board at some point and see if it makes sense to you after you practice it for a while. So I'll be giving you these problems going forward. If the lesson sets I have didn't introduce it at this point in time, then I'll make one up. All right, and that takes care of that. All right, so now let's get some practice in. This one was a U substitution problem, so you should do it as a U substitution and change the limits of integration, and I'll do that again the next time. Right now we'll just integrate it and see what the area under this curve is from 2 to 5. So you're stopping the video. I am going to need a new cartridge here in a second. Can I get away with this one? All right, that's a good one. Let's switch. All right, so we're going to integrate from 2 to 5. Oh, I like that. Square root of x minus 1 dx. And let's do it out. You try it. The first thing I'm going to do is rewrite this as x minus 1 to the 1/2. I'm going to integrate that, which is x minus 1 to the 3/2, dividing by 3/2, 2/3. And now I'm going to go from 2 to 5, plugging it in. 2 to 5 minus 1, 4, square root of 4, 2, 8, 16/3. 2 minus 1, 1, so 2/3, 14/3. The next time I do this problem, I'm going to change the limits of integration and remember that answer. So tomorrow, not tomorrow, it'll be two worksheets from now, I'm going to come back and let's see if my memory holds. I hope so. So I'm losing my memory. All right, so one has been done. 3 trapezoids for f of x from 5 to 9. Well, from 5 to 9 is a width of 4, and we want 3 trapezoids, so we're looking at 5 to 9, 3 trapezoids, so 4/3. Why is my brain so slow? So 15/3 plus 4/3 gets me 19/3 plus 4/3 gets me 23/3 plus 4/3 gets me 27. Okay, so this works. And so the altitudes are going to be, for instance, f of 19/3. Okay? And so we're going to have something that maybe looks like this. All right? And there's my 3 trapezoids. The ones in the middle get used twice. The one at the end and the other end are used once. And so the widths are 4/3. And I have to do a trapezoid, so I'm going to use left and right hand rectangles. So 4/6. So 4/3 divided by 2 would have been better stated as 2/3 divide the 4 by 2. So 2/3 times, cut to the chase here, f of 5 plus 2 times f of 19/3 plus 2 times f of 23/3 plus f of 9. And that's estimating the area under f from 5 to 9. Okay. Done enough of those. I don't think I need to say anything else. So there's our 3 trapezoids. As we go to infinity, hopefully from your algebra practice, you know this goes to 5/2, and I don't have to talk about that too much. But what I will do is give you a quick rendition of 5x cubed. So x cubed might look like this. 5x cubed is every single place, every altitude is multiplied by 5. So this function multiplied by 5, going up and going down, much faster, much narrower, right? And if I was going to do 2x cubed, I'd be doubling these. So I'll put dots doubling these, right? And that's going to be that graph. Well, what happens as we go to infinity is we get constants of proportionality here. That this is going up 5 times as fast as that one. That's our answer, right? This is equal to 5/2. And so L'Hopital saw this, and as we move to infinity, I probably could get a better drawing, but this starts to look like a slope, and this starts to look like a slope, right? And the slopes share the change in x. So if you have a fraction, let's say that that's 5 over, let's say that's 3 units, and you divide that by 2 over 3, well, what's going to happen to the 3's? Right? 5/3 times 3/2. They're going to cancel out of the problem. And that's why you can divide one derivative by another. Anyway, if you want to see how L'Hopital works, if you're coming into these practices having had some calculus and we've been working with L'Hopital, you might as well go look at why it works. And that's in the playlist. Okay, so that takes care of that one. Should go to infinity. So f of x, we want to rewrite f of x as x to the 4/5 minus x to the minus 2 minus x to the minus 2 is another way of writing that. So its derivative is, let me make sure, am I integrating? No, I'm taking a derivative. Okay, so this is minus x to the minus 2, so this is going to become positive 2 x to the minus 3. And that's what little f of x is going to equal. Okay, did I take this derivative yet? No, I haven't taken this derivative yet. So that's 4/5 x to the minus 1/5, right? Got to subtract 1, 4/5 minus 5/5. Woo! Okay. Been up for a while now. But the fog is still burning off, so I got up really early. Bounded area. 2x to x squared minus 24. X squared minus 24 is a parabola that looks like that. That's 0, -24 for a vertex. And 2x looking like that. So we get an intersection over here, and we get an intersection over here. So we got a factor, x squared minus 2x minus 24 equals 0 to find those. And we can see that a 6 over here and a -4 here looks to be right. Let's check it with the 6. 2 times 6 is 12. 36 minus 24 is 12, so those are correct. I have a top function and a bottom function, and I'm going to create one little slice of bread right here. Okay, so top minus bottom, integrating from -4 to 6, left to right. Top function, 2x. Bottom function, x squared minus 24, dx. We're not going to do it out, okay? But that's the calculation you'd be working with. Number 6, you're pausing the video, trying to find y prime. Okay, what's y prime? Well, we got a product rule because this is multiplication, and we got a little bit of a chain. So I got to get f prime of x, derivative of the first, times, leave the second alone. Now, add to that the derivative of the second function, which is g prime of h of x times h prime of x, and leave the first one alone, f of x. Boy, running out of room here for that one. That takes care of that. Let's get that out of the way. Can you do that one in your head yet? Probably not. But what kind of function throws x squared plus 5 into the denominator? I'm hoping this comes to mind. And you can do u substitution here. You can take your time with it. Let u equal x squared plus 5. You do that out. But if you took this derivative, and I should put a plus c here, if you took this derivative, we would have 2x over x squared plus 5, right? Been talking about the ln of f of x. Derivative of that is f prime of x over f of x, right? But I got to make that a 6. Just did. All right, next problem. Somebody called me on my phone, but I'm not going to answer it. I am just going to do these problems out right now. So y prime for this one. Can you see it over here? Let's see. Let's bring it this way a little bit, then I can do it right above it. I don't like the angle this board is at. trying. So I'll rewrite it. I've got the function tan. You do that to me, board. Tan cubed of 5x to the 4th. So the derivative of that is 3 tan squared 5x to the 4th. Derivative of tan, secant squared 5x to the 4th. Derivative of 5x to the 4th, 20x cubed. Little practice there. All right, now we're going to knock off an implicit differentiation problem. 4x minus 2x squared y plus y to the 5 equals 1. I got 4, the dx's cancel. Minus 4xy, the dx's cancel on the product rule. Minus 2x squared y prime. dy divided by dx gets us that. The dy here gets divided by dx, so 5y 4 y prime equals 0. I can factor out y prime over here, minus 2x squared plus 5y to the 4, right? I can factor that out. I still have 4 minus 4xy plus that. So moving everything to the other side and isolating y prime gets us minus 4 plus 4xy all over minus 2x squared plus 5y to the 4. I hope I'm not making any careless errors. All right, next problem. Then you pause the video wherever you need to, look at it, think. So I'm asking a question about how many points of inflection does big G of x have? How many pi's? Okay, and I'm giving you this notation. Well, I think we have G, I think we have G, and I think we have that. Position, velocity, acceleration, perhaps. All right, but I'm taking the derivative of that, so that's another way of writing this. So this is a second derivative. G prime is equal to x squared times x minus 3, and you need to know what that looks like. So I don't usually draw the y-axis. I don't know why I did there. So we have a root at 0 with a vertex looking, wow, situation. And a linear cut through 3. So this is going to infinity when I put big numbers in. So this is what your graph looks like. And we're looking at the second derivative. And the calculus says when the second derivative is negative, we're concave down, and when it's positive, you're concave up. And it's when we have one of those changes, positive to negative or negative to positive, that we get a point of inflection, and that only happens here. All right, I'm concave down, then I have a slope of 0, and I'm concave down again. We don't call that a point of inflection. It's when it changes concavity. And that only happens at x equals 3. So there's one point of inflection for big G. All right. Nice concepts we're talking about. Slowly building a little conceptual awareness, I hope. All right, 10 more problems. I think I got 20 problems, and then I'll overload the next one with like 27 problems. And hopefully some of it will go quick. Back to the wall. Yeah, feel like Game of Thrones here. All right, so what do we have? We've got a concept that's going to need to be developed, and if you understand it, you've come a long ways. When you can write a function using an integral expression, you have made some gains. So let's see if you can try it. All right, so what's an easy number to plug in here? I think 0. 0, 0, and the cosine of 0 is 1. I think I can write a 0 here, and I think I can write a 1. Let's see, I'm going to move this a little bit. Oh, bored. Behave. Behave. I feel like I'm talking to my dog. All right. 0 plus 1. I am going to accrue area under a curve. What curve? Its derivative. So that's 2x, but I'm going to use some dummy variables here. I'm going to say 2t, right, plus 4 minus sine t dt. These are all altitudes, contributing altitudes plus 1. Now, I will do a much simpler situation than this. I'm just starting the conversation. And when I start a conversation, I breeze through it because brain's not going to process it immediately anyway. All right? But if we can move it a little bit and then come back at it, and then maybe do a situation that becomes really seeable, then we can work with more problems and build our kind of like times tables accuracy. All right, so that's that. And I will be developing that concept as we go along. All right, can you do that one in your head? Can you do integral of secant 4x tan 4x dx? We did another one that was similar to it. I hope you know that this comes from the secant of 4x plus c. And we just got to figure out if I took that derivative, I'd have a times 4 here. I don't see a times 4 here, so it's 1/4. Now, I'm doing these a lot faster than I did 2 weeks ago. I was stumbling. I hadn't done calculus in a while and trying to get back into the swing. Flowing a little better. 13. Find magic C. Magic value for C here. Mean value theorem for derivatives. What does it mean to you at this stage? I hope it means where does the average rate of change equal the instantaneous rate of change? Where it's got to be at least one place, provided the function's continuous, which it is, and it's differentiable everywhere. That's basically what's going on. So I got to put a 0 into this function, and I get a 0 out. I got to put a 4 into this function, and I get 64 minus 12, 52. I divide 52 by 4, and I get 13. So the slope is going up at 13 to 1. From that location to that location, and it looks like that would be actually not a very good graph. This graph looks like this, right? And so from here to here, 13, 1. There's got to be at least one place where I'm going up at the same rate, right? There is one place here. How do we find it? Well, we set this 13 to 1 to the derivative. We get our slope, and the slopes are 3x squared minus 3. So we only want the positive what? 16, oh, 12, sorry, 10 thirds, square root of 10 thirds. Is that number between 0 and 4? Certainly is, okay? And that's where this is going up at 13 to 1. Near the number, what, 1.5? It seemed to happen really quickly. Did I make a mistake here? 3x squared minus 3, adding 3. Oh, adding 3. I subtracted 3. I thought I was making a stupid error just based on what I looked at there. That's why it's good to do things from different perspectives. If you ever check your work, try to remember to do it 2 different ways. All right? Because you're going to make the same mistake. If you do it the same way and you check it the same way, you probably make the same mistake. All right? So this was 16 thirds square root, just the positive. There's another time I'm going up at 13 to 1 over on the left, but it's not in that interval. So 4 thirds, a little bit more than 1. It still seems a little off to me, but pretty sure that's right. All right, so maybe I'll look at that more carefully on my own time. Okay, minus x over y, 0, 2. Got a feeling we're looking at x squared plus y squared equals 4. Okay, so let's find out. Let's move our variables into the integration perspective. Let's integrate. This is going to be y squared over 2. This one's going to be minus x squared over 2 plus c. Let's throw our 0 in. 0 goes. Let's throw our 2 in. And yes, that's 4. Oops, I made a mistake here. That's good. I'll remember that the next time, because that 4 should have been an 8, I believe. No, it's a 2 right now. I'm already doubling in my mind, right? 0 gave me 2. 2 squared 4. Okay, that's fine. So now I'm going to bring that over, and there's my x squared plus y squared equals 4. Now, if I solve for y here, if I solve for y, I'm going to get plus minus, but I'm just going to look at the square root on the positive side right now. I'm going to get 4 minus x squared. Now, what's the derivative of 4 minus x squared? It's minus 2x on the inside over 2 times the square root of 4 minus x squared. What happens to the 2's? They cancel. What's another name for y equals the square root of 4 minus x squared? I think it's y. And do you remember it? The original problem had minus x over y as the starting point. Okay, well, it doesn't hurt to see that. Local min for x cubed minus 5x squared minus 8x plus 4. So when we're finding local mins and local maxes, right? Well, what can we say? Slope 0, slope 0, slope 0, so on and so forth. So I think I want to find the slopes of that curve. And hopefully you can see that well enough. Yeah, now you can. So we got 3x squared minus 10x minus 8 equals 0. I wouldn't have given it to you if it wasn't factorable, so let's go factor it. Looks like I have a minus 4 and a positive 2. So I have a quadratic that cuts through at 4 and at negative 2/3. This is measuring all the slope values of that cubic. And these are positive slope tangents, negative slope tangents, positive slope tangents. So I have a function that's going up, then it's coming down, and then it's going up again. Up, down, up. So I'm looking at the right-hand side where my derivative changes from negative to positive, and I only want to know the x value here. If I wanted to know the y value, I got to plug 4 into the function, and I'm not gonna. Because I got to upload this video and I got to be somewhere in about 20 minutes. Tangent x plus y equals 2x. Can I do it over here and save some time? I hope so. Derivative of tan is secant squared of x plus y. Derivative of what's inside is times 1 plus y prime. And that's going to equal 2. The rest is all algebra. Multiplication becomes division, so that's secant squared x plus y. I have moved it. How do I get y prime alone? Additional 1 simply becomes subtraction of 1. And we got some practice. And yes, did I line up my equal signs? Did I write everything out? No, because what am I after? You thinking. Right now, just going after you thinking. G of x equals x squared plus 2x. Plus, oh God. X squared divided by 2x. Quotient rule. All right, low. D high. Minus high. D low. ln of 2 times 2 to the x. A little practice there. All over low, low. 2x gets squared. So that's the same thing as 2 to the 2x, like multiplication. All right. Now, what I really like to do in a class is, after I present something, come back at you. So here's an inverse. Let's say that f of x is equal to, oh, I don't know, x to the 5 plus 2x. Very similar to the last problem. And I want to know, that's too big. So let's put it here. X to the 4 plus 2x. Okay. So it's something that you can work with. So I want to know what g prime of g prime of 20 equals. Well, I hope up here, you're pausing the video, I hope, and you're trying to remember what we did 20 minutes ago, that's going after your long-term memory. All right, so 2 to the 4 is 16 and 4 is 20. So when does this thing equal 20? F of 2 gets me 20. And what's the derivative at f of 2? Let's find out. 4x cubed plus 2. Put a 2 in, 32 plus 2 is 34. Are you ready to tell me what g prime of 20 is? 1 over 34. Okay? A little repetition there. Made you think back to what we did at the beginning. So I've got g of x is equal to x times 4 minus x cubed, and I didn't say what I'm looking for. So let's find out when big G is going up. All right, so that's the first derivative. Let's graph it real quick. I get sine change, linear cut at x, cubic cut at 4, cubic cut at -1. Putting a big number in, this is going to be negative. So I'm actually believe I'm going down, and I didn't do the cubic cuts, but I just wanted to find out where I'm positive, and that's -infinity to -1, 0 to 4, union, 0 to 4. At 0, at 4, at -1, my graph is flat. Okay, so we had 3, they were all odd. So 3 cuts through the x-axis, 3 changes signs. I don't like to say bottom heavy and things like that. I like to say exactly what it is. We had 3 sign changes at those locations. Okay, big F. Similar question, I think. I'm giving you f prime, so that's a second derivative. The ln of x is the second derivative. ln of x cuts through the x-axis at 1, 0. And I want to know when I'm concave down. Well, that's what I asked. And I've got a second derivative. So second derivative is negative from 0 to 1. So x has to be less than 1, but greater than 0. ln of 0 is undefined. And so that's when this function would be concave down. One more problem. Yippee. Just the calculation that finds the area bounded by e to the x, y equals 9 and 0. We did 10 yesterday, I think. Now we're doing 9. Did you remember to do this? Okay, so we're going to go from 0 over here to what? We got to solve when does e to the x equal 9, and that's the ln of 9. You put the exponent on top of e to get you 9. If you put it on top of e, it's going to get you 9. You should hear that from time to time. So top minus bottom for one slice of bread is 9 minus e to the x. From what to what? From 0 to ln of 9. dx. There's the calculation that finds this area. First quadrant. First quadrant area, because x equals 0 is the x-axis. Right? That's x equals ln of 9. Now what would it be if we wanted to do it with horizontal slices? Well, then I have to define x in terms of y. So these things become y. And we have to go from what? 1 up to 9. So we're integrating from 1 to 9. And it's top minus bottom becomes right minus left. What is the right-hand function? The right-hand function is x equals the ln of y. All right, so we have the ln of y minus 0, which is on this side, dy. Pretty soon we're going to be making cones and all kinds of things. All right, so a little bit of practice, and I'll upload that later today when I get a chance to do it, because I'm heading out the door right now, so I'll do it later, and have a great day.